In today's class, we shall be analyzing the mass on an inclined plane with a pulley. And this time around, we're going to be assuming there is friction. So there exists a frictional force. In our previous video, we have established the equation connecting the tension on the two strings that is holding the two masses. And then we also assumed that there was no friction. But in today's video, we shall be assuming that there is friction. And if there is friction, what is going to happen? So if there is friction, it's only going to affect the mass that is on the surface, on the inclined plane. This one is hanging through the air, so there's no friction obstructing the movement of M2. But for M1 that is on the surface of the plane, it is going to be affected by frictional force because we are assuming that the surface of the plane is not smooth enough, it's a bit of rough, so the friction is going to attack them. Then what do we know about friction? So the friction on inclined plane, feel free to check out my video on frictional force so as to understand fully everything you need to know about frictional force on an inclined plane. So from what we've discovered, we already know that the frictional force is given as the coefficient of friction multiplied by the normal reaction. And for an inclined plane, the frictional force there is given as mu. The normal reaction is given as mg cos theta. So these two equations are going to come handy in helping us to figure this out. And we also know that for the frictional force in this situation, this is what we have as the case. So let's go ahead and get the equation that are relevant for this system. So the first thing we're going to be analyzing each of the bodies. So by drawing our free body diagram. So let's start with M2. So M2 is pretty, if we check M2 is very free. If you have been following this class, you know it's very free. So M2. Now, if you look at the direction of the arrow, you can agree with me that this is a case where M2 is greater than M1. So that's the case we are dealing with where M2 is greater than M1 and there is friction. So M2 has these forces acting on it. The first force that's acting is the weight acting downward. The next force is the tension pulling it upward. And eventually the equivalent for the resultant force of the system is heading downward. So to get the resultant effect produced by these two forces, we need to subtract the tension from the weight since everything is going down. So in that case, we are subtracting the tension from the weight. So we'll have W, who is the upper hand, minus the tension. That will give us the resultant effect. So if we break that down, is M2 multiplied by G minus the tension, and that will give us the mass M2 and the acceleration of the system. So if we make T the subject formula, we will have that T is going to be equal to M2G minus M2A. So what did I do? I simply interchange the process. So just minus T goes to the other. So just subtract RT on both sides and subtract M2A from both sides. You get that? So now we've got this. This is our equation 1. So this equation is kind of similar to the one we derived when there was no friction. So it's kind of similar. The tension for whether there is friction or not for this particular mass, M2 hanging here, remains the same. But then let's look at M1 when there's friction. So for M1, so we already know the forces that are acting on this system. What are the forces? The first force is tension. It's pulling it this way. See, this is tension acting this way. Now, if there another force that's going to put the weight, we have the weight component that's acting this way, which we already know is W sine theta. That's the weight component that's acting down this way. Now that friction exists. Now friction is going to oppose the movement of the force, the resultant movement of the force. So where is this mass eventually heading to? So according to the arrow, the whole process is moving upward. So which means the resultant, if the resultant effect is heading upward, it means that the frictional force is going to be acting downward. So you can see that the frictional force is combining with the weight in this direction to act downward. So that's the forces that are acting on M1. So we can see that the weight component is acting down this way, W sine theta. The weight component, feel free to check out my previous video to understand how this works. So the weight component is acting this way. The tension is heading this way. and the tension, it seems to be winning as it is dragging the entire mass up the hill. And because it's winning, the frictional force is trying to stop it from achieving the process by also heading this way. So we can see what's going on here. So apparently, for us to get the resultant effect of everything, regardless of friction, the force was moving this way. We can see that the tension is the higher force. If we subtract the frictional force and the weight, we can see two of them are working together. The weight component and the frictional force are combining together, dragging this down the hill, but tension overcame all of them, and everything was moving up the hill at a resultant of m1 multiplied by acceleration of the system. So if we expand on this, we have t minus w is m1g sine theta plus, what is our frictional force? The frictional force for the system, look at it here, is given as coefficient of friction mg cos theta. So, and that is equal to, let me write it down here, it's equal to m1 times the acceleration. So now this is it. So we can also break it down further by, let's make t the survey formula. If we make t the survey formula, we can see that t is equal to m1 times acceleration plus the two forces, which is m1g sine theta plus the frictional force, which is mu mg cos theta. So this is it. So now this is the second equation. This is the case where there is frictional force. You can see that it's not really a much of a deal. If there is frictional force, the frictional force is going to add up with this guy. You can see the frictional force here. So if we are looking for the acceleration as well, all we need is to combine the two equations. So if we do that, we are going to have m2g minus m2a. We are putting it into this equation t because that's equal to t. So we are taking the value of t and putting it right here, so that we have this is equal to m1a plus upper bracket m1g sine theta, which is the weight of m1 pulling it in that direction. And then we have the coefficient of friction mg cos theta, which is the frictional force pulling in the right direction. So we can collect the like terms here. We have that m2g minus everything inside the bracket is m1g sine theta plus coefficient of friction mg cos theta. So this will be equal to m1a plus m2a. So we can factor out a. So if we do that, let me wipe this. So if we factor out a, we'll have m2g minus upper bracket m1g sine theta plus mu mg cos theta, and that is equal to the acceleration a all in m1 plus m2. So as usual, all we need is just to do what? Divide both sides by the coefficient of a. So I will divide here by m1 plus m2. So I'll also do the same for here, m1 plus m2. So if we do that, we can see that the acceleration is equal to m2g minus m1g sine theta plus coefficient of friction mg cos theta. This divided by m1 plus m2. So that is the case for the situation like this. So remember the m here, this mg cos theta has always been the m1g. Remember, it is the m1g as the case may be. The mg, that's the frictional force in the mass 1. That's the m1g, that's the mass resting on the inclined plane. So it is m1 g cos theta. So that is the way to ascertain the acceleration in the system. So that is it for today's class. I'll see you guys in the next class.